Animation blending techniques are essential for creating smooth transitions between different animations in game development. By understanding how to combine multiple animation clips effectively, developers can deliver a more immersive and engaging experience to players. In this session, we're going to explore the fundamental components behind animation blending. We'll focus on animation clips, their structure, and the methods used to blend them seamlessly. Think of animation clips as the building blocks of your animations. When you layer and blend them together, you're essentially crafting an experience that feels natural and lifelike. Let's dive into the details. First, we'll break down the structure of these clips. Each clip contains keyframes, which are the specific points in time where the animation changes. Understanding this is crucial as it allows you to manipulate timing and movement. Now, when it comes to blending, there are different methods like linear interpolation or additive blending, each offering unique benefits depending on what you're aiming for. So, whether it's a character leaping gracefully or a camera panning across a scene, mastering these techniques will definitely elevate your game design skills. Let's get into it. As we dive deeper, let's first clarify what constitutes an animation clip. Animation clips are really neat collections of keyframes that capture significant moments in an animation timeline. Instead of storing transforms for every single frame, that would take up a lot of space. An animation clip focuses on the keyframes necessary for smooth playback. This method not only conserves memory, but also makes animations way more efficient. Each animation clip typically consists of a series of time-stamped transforms that dictate how a model should position itself at specific intervals. Now, picture this. Imagine a character that needs to transition from walking to running. Here, we would actually create two separate animation clips, one for walking and the other for running. By capturing just the keyframes, we can smoothly manage the transition between these states through interpolation of the transforms. This results in fluid motion rather than those jarring, abrupt shifts, something that's super important for achieving realism in animations. Now, let's explore how we can implement linear interpolation in C++ to facilitate smooth transitions between keyframe positions in our animation clips. The function blendPositions takes three parameters, two glm.vec3 types representing the starting and ending positions of the keyframes, and a float alpha that dictates the blend between these positions. Inside the function, we have this return statement that uses a simple but effective formula to compute the blended position. By multiplying the starting position by the value of 1.0f minus alpha and the ending position by alpha, we effectively mix both positions based on the value of alpha, which ranges from 0 to 1. So, when alpha equals 0, the function yields the starting position. If we have an alpha of 1, it gives us the ending position. Now, values of alpha in between invoke a proportional blend of the two positions, allowing for a gradual and natural transition. This approach embodies the essence of animation blending, enabling developers to create cohesive motion between different states or actions seamlessly within their game environment. So, the displayed figure, titled Animation Blending Techniques, Walking versus Running, plots the influence percentage of two animations, walking in blue and running in red, against the blend parameter labeled alpha, which ranges from 0 to 100. Key patterns are readily observable. The walking influence starts at 100% when alpha is 0 and then decreases non-linearly as alpha increases. On the other hand, the running influence begins at 0% and increases non-linearly toward 100% as alpha approaches 100. Now notice the shapes of these curves. They're not straight lines, but rather concave, indicating a quadratic weighting of each animation's influence instead of a linear blend. For instance, at alpha equals 50, the plot indicates that walking has roughly 75% influence, while running sits around 25%. This asymmetry happens because the curves function as squared terms of the blend parameter, creating a bias towards walking for much of the range. Interestingly, the two curves only achieve equal influence at approximately alpha 70.7, where those quadratic terms balance out. So, running, it doesn't take the lead until we push the blend parameter significantly toward its upper end. From this visualization, we can conclude that using a quadratic mapping for blend weights results in a slower and smoother transition from walking to running, which helps preserve walking motion across those mid-range alphas. Plus, the choice of curve shape directly influences responsiveness. A quadratic curve actually reduces sensitivity at lower to mid alphas, delaying the transition later on. This can be quite useful to avoid those premature or jittery switches between different gate animations. Finally, you'll see the legend, grid lines, and ticks at 10-unit intervals provide precise readout points, making it easier to evaluate specific alpha values and their corresponding influence percentages when fine-tuning blend behavior. Finally, you'll see the legend, grid lines, and ticks at 10-unit intervals provide precise readout points, making it easier to evaluate specific alpha values and their corresponding influence percentages when fine-tuning blend behavior.
Now, let's take a look at the implementation of spherical linear interpolation, or SLIRP, which we use to achieve smooth transitions between quaternion rotations. In this function, the first step is to compute the dot product of the two quaternions, start and end, to determine their relative orientation. Now, if the dot product is negative, indicating that the quaternions are pointing in opposite directions, we need to reverse the end quaternion to ensure a smooth rotation. Next up, we introduce a threshold value. This helps us decide whether to use linear interpolation instead. So, if the quaternions are close enough, meaning the dot product exceeds our threshold, we can just stick with linear interpolation to keep things efficient. We will normalize the result to make sure it remains a valid quaternion. On the other hand, if they're farther apart, we need to calculate the angles required for SLIRP. These angles are derived using the arc cosine of the dot product, which gives us the angle between the quaternions, adjusting it by the blend factor alpha. Finally, we calculate the relative quaternion and use trigonometric functions to combine the two quaternions elegantly. This entire approach guarantees a smooth transition, avoiding those potential artifacts created by simpler methods of interpolation, resulting in a visually appealing rotation for character animations.
Now, let's dive into how we can represent blend spaces in our animation system, which is a really cool topic. We start with the blend space struct, which brings together the core elements necessary for blending animations. This structure holds a vector of animation clip objects. These are essentially the animations we want to blend into one seamless experience. Within our blend space, there's also a position variable that represents the input parameters for blending. It's laid out as a two-dimensional vector, allowing us to define our blend space across two axes. This really amps up the complexity and fluidity of our character animations, making them feel much more lifelike. Now, moving on, we implement a method called getBlendedAnimation. This is crucial for grabbing the animations that match our current blend space position. So, here's where it gets interesting. We're going to take a somewhat simplified approach by selecting two clips, clip A and clip B, from our vector. These selections would usually depend on the actual logic of our blend space positioning. Moreover, we calculate an alpha value based on the position.x, which decides how much weight each clip has on the final blended animation. Finally, to wrap everything up, we call the method blendAnimationClips to mix these two clips together, resulting in dynamic and responsive animations that react intuitively to player input or game states. Pretty neat, right? Now, let's see how we can implement dynamic animation blending within our game loop. In this update function, we first retrieve the character that represents our player. This not only allows us to interact with the character's properties, but also prepares us to apply the blend logic effectively. Now, let's take a closer look at what needs to happen next. We extract the player's current speed by using the getSpeed method. This speed serves as a vital input for our blending calculations. It's essential to normalize this value to fit within the defined blend space range, right? By clamping this normalized value between 0.0 and 1.0, we ensure it stays within the necessary boundaries for blending. This way, we avoid any unintended jerky transitions. Following this, we update the position of our blend space based on the player's speed. You see, this mapping is absolutely crucial as it directly influences which animations will be blended and how smoothly those transitions occur. Finally, we retrieve the blended animation clip by calling the getBlendedAnimation method. This allows us to access the smoothly transitioned animation that corresponds to the current player speed. After that, we instruct the player character to play this newly blended animation, creating a dynamic and responsive visual experience as the game environment evolves. It's all about making the game feel more alive, right? Slightly excited. The code starts with a function that generates a noise value using a simple sine wave as a placeholder. This function produces values oscillating between 0 and 1, which creates a nice variability in the blending position over time. By using a sine wave, we ensure smooth and continuous variation, allowing for those more organic transitions between animations. Next, we have the update function, which gets called within our game loop. This function calculates the current noise value by passing the game's current time into the noise function. The resulting value is then mapped to our blend space's position, specifically affecting the X component. This integration of procedural noise alters our blending parameters dynamically, introducing an element of unpredictability to those animation transitions. Now, as the game progresses, this approach helps create animation outputs that feel more lifelike and less mechanical, ultimately enhancing immersion. By incorporating these procedural techniques, we can achieve complex and nuanced animations that evolve naturally throughout gameplay, adjusting to character movements and interactions without needing manual tweaks for every situation. Finally, as we wrap up our lesson on animation blending techniques, it's super important to highlight the necessity of testing and refining those animation blends. You see, fine-tuning means adjusting those blend parameters and really evaluating how they perform across various game scenarios. This iterative process is key to making sure that animations not only look good, but also feel right within the gameplay context. So far, we've dove into the significance of animation clips, explored the theory behind interpolation techniques, designed blend spaces, and weaved these concepts into a game loop. Moving ahead, we'll shift our focus to performance optimization techniques as we dig deeper into more complex animations. We'll also take a look at some additional tools that can help developers achieve a greater level of fluidity and realism with their animated characters.